Hi there, this is your favorite non-Indian math channel, and I have a nice recurrence relation problem for you. So let's see how we can do it. Well, I'm given that a and b's are both positive, a is bigger than b, a1 is given, and here what I can notice is that I have an minus 1 terms at the denominator, and therefore this thing cannot be linear. So what we have learned before will not work here. And so let's try to use another method. Well, this method would work in general, but there is nothing special about it. So we will basically try to write like first few terms, and we will try to spot a pattern. So let's write, so I already have a1. Let's write what is a2. a2 is going to be, so I'm just putting n is equal to 2 here, a plus b minus ab over, so a1 minus 1 is just a1, which is a plus b. So if I just expand this, it's going to be a squared plus b squared plus 2ab minus ab is just going to be a squared plus ab plus b squared over a plus b. Okay, cool. Well, of course I don't see something yet. We need to do it at least one more time. And a3, sorry. So I'm putting n is equal to 3 here. It's going to be a plus b minus ab over. So a minus 1 is going to be a2. So I'm just going to flip this thing. It's going to be a squared plus ab. Sorry, it's just ab, ba plus b squared. And I'm going to get an a plus b here. So here, let's try to just write everything a bit more expanded already. I don't want to go all the way to the right side. So this thing is just a squared b plus b squared a. So if I just expand this thing and just multiply it with this one, I will have a cube plus b cube. This will be, so I will have a squared b. Here I have minus a squared b, so they will cancel. Same for this a b squareds. And I will just have an b squared a. So I will have only one of them left. A squared b plus b squared a. Okay. And at the denominator, I just have this thing, a squared plus ab. Here, well, yeah, it seems like there is a pattern. And here, if I look, all of these powers, I have 3, 3, 2 and 1, 2 and 1. All of these powers are adding up to 3. And here is just 2, 1, 1, 2. They're also adding up to 2. And here, if you remember the cubic formula, a cube, so I have all of these signs are positive. So I'm going to write a cube minus b cube. This is a minus b times a squared plus ab plus b squared. So here what this suggests me that if I just multiply this thing by a minus b and divide it by that, and this is where our assumption is coming from. If a was equal to that, we couldn't do such stuff, and we would need to just do different operations, okay? And here, so I can just multiply and divide it by that, and they're just positive. So what will I have is that at the denominator it's going to be a squared plus, so it's just going to be this thing, a cube minus b cube. And for the top part, well, it's not so obvious. It's a to the 4. I will have minus b to the 4. Let's write these two first. And so then, let's see. I have minus a cube b from these two. And from, so it's minus a cube b. And from this one, I will have plus a cube b. So, and similarly, all of these ones will just cancel. You can do the algebra part. It's just clear. It's one step. And so this is equal to a to the 4 minus b to the 4 over this thing. And if I look at here now, so if I again just do the same trick, I'm just multiplying it and dividing it by a minus b. So this thing is just a cubed minus b cubed. And this is just difference of squares. It's just a squared minus b squared. Well, now I obviously have a rule. If you look, a2 is just this thing, and it's just increased by 1. It's difference of cubes, and here is difference of fourth powers. And so I can guess that my solution for an, so it's just one extra for the top part. It's an plus 1 minus b to the n plus 1 over a to the n minus b to the n. And if I put here, like I'm trying to see, is this true for any n? If I put 2, of course this is true. If I put 1, it's gonna be over a minus b. It's gonna be a squared minus b squared. It's gonna be a plus b. If you put n is equal to 1 here, it's gonna give you a squared minus b squared over a minus b, which is equal to a plus b. So this is true even for a is equal to n is equal to 1. So we can say that n is greater or equal than 1. And well, this is the best we could do. But it wouldn't matter if this was greater or equal than 2. It would be totally fine if this wasn't holding for n is equal to 1. So let's see. Well, I'm saying that an is equal to this thing, but I actually should prove it because I only did it for 2 terms, for a2 and a3, and I guess that my solution is this, but this is not a proof. So we can, and the easiest way is to show this by induction. And let's see how this goes. So I already did the base cases. I did it for a2 and a3. It's also true for a1. And so let's say that a2 is true. Let's show this for n is greater or equal than 2. Well, it's just same. Okay, let's show it for 1. And I'm gonna say that this is just Pn. So Pn is the case that this holds. Okay, so I'm saying that P1 for A1 holds. Okay, so P1 holds is true. And now the second case, second step of induction is let Pn holds. So let Pn is true. Be true. Okay, let's use correct English. And let Pn be true. And then we are supposed to show that is Pn plus 1 true? Is this true? Okay. So this is our goal. We already accepted this. Well, we know that this is true. We are assuming that Pn is true. And now we are going to show Pn plus 1 is true. So here, what do I mean by Pn be true is that, so this thing is literally true. We know that An is equal to this thing. So we say now, okay, I'm accepting this. But I should also show it for the next term. So let's write An plus 1. So by our like recurrence relation, this thing is just gonna be a plus b minus ab over. So I'm just putting n is equal to n plus 1 here. So this will be an, which is this thing. So I'm just gonna flip this thing. It's gonna be a to the n plus 1 minus b to the n plus 1. And here I have a to the n minus b to the n. And let's just do this. So I will have, let's do this part. It will be a to the n plus 2 and minus b to the n plus 2 minus a to the n plus 1. Sorry, it's just plus a to the n plus 1b minus a b to the n plus 1. So this is from this part, and from this part I will have minus. It's gonna be a to the n plus 1b and minus a b to the n plus 1. And here I can notice that this a to the n plus 1b is just same with this. They have different signs, and here this is also positive sign, so this still will also cancel. And so I have just everything is here 0. This is a to the n plus 1 minus b to the n plus 1. So I'm just going to delete this part to make it look a bit more clear what we have found. And so I found that a to the n plus 2 minus b to the n plus 2 over a to the n plus 1 minus b to the n plus 1 is equal to a n plus 1. And here, if I just compare this stuff, and so this is literally just, if I put n is equal to n plus 1 here, I would get exactly this thing. So this is indeed true. We would just get the same property for an. If it's true for an, we would just find an plus 1 with the same rule. So this rule is correct, and this is our answer.